Hey there, amazing people. I'm thrilled to have you here today. Welcome to another exciting video where we'll be shedding light on implicational propositional calculus. In mathematical logic, the implicational propositional calculus is a version of classical propositional calculus that uses only one connective, called implication or conditional. In formulas, this binary operation is indicated by implies, if, then, and so on. Let's now venture into the realm of functional incompleteness and explore the fascinating intricacies it holds. Functional incompleteness. Implication alone is not functionally complete as a logical operator because one cannot form all other two-valued truth functions from it. For example, the two-place truth function that always returns false is not definable from an arbitrary propositional variables. Any formula constructed from an propositional variables must receive the value true when all of its variables are evaluated to true. It follows that is not functionally complete. However, if one adds a nullary connective for falsity, then one can define all other truth functions. Formulas over the resulting set of connectives are called F-implicational. If P and Q are propositions, P is equivalent to P, PQ is equivalent to PQ, PQ is equivalent to PQQ, PQ is equivalent to PQQP. Since the above operators are known to be functionally complete, it follows that any truth function can be expressed in terms of AND. As we transition to the next segment, let's unravel the mysteries surrounding axiom system and gain a fresh perspective. The following statements are considered tautologies irreducible and intuitively true. By definition, axiom schema 1 is PQP. Axiom schema 2 is PQR PQPR. Axiom schema 3 Peir's law is PQPP. The one non-nullary rule of inference modus ponens is from P and PQ infer Q, where in each case P, Q, and R may be replaced by any formulas that contain only as a connective. If is a set of formulas and R formula, then it means that it is derivable using the axioms and rules above and formulas from as additional hypotheses. Łukasiewicz 1948 found an axiom system for the implicational calculus that replaces the schemas above with a single schema QRRPSP. He also argued that there is no shorter axiom system. Let's now venture into the realm of basic properties of derivation and explore the fascinating intricacies it holds. Since all axioms and rules of the calculus are schemated, derivation is closed under substitution. If a, then ea. Whereas any substitution of formulas using only implication. The implicational propositional calculus also satisfies the deduction theorem. If a b, then a b. As explained in the deduction theorem article, this holds for any axiomatic extension of the system containing axiom schemas 1 and 2 above and modus ponens. Let's transition to completeness and uncover its significance. The implicational propositional calculus is semantically complete with respect to the usual two-valued semantics of classical propositional logic. That is, if is a set of implicational formulas, and it is an implicational formula entailed by, then a. As we transition to the next segment, let's unravel the mysteries surrounding proof and gain a fresh perspective. A proof of the completeness theorem is outlined below. First, using the compactness theorem and the deduction theorem, we may reduce the completeness theorem to its special case with empty, i.e., we only need to show that every tautology is derivable in the system. The proof is similar to completeness of full propositional logic, but it also uses the following idea to overcome the functional incompleteness of implication. If a and Fahrenheit are formulas, then is equivalent to where it is the result of replacing in a all, some, or none of the occurrences of Fahrenheit by falsity. Similarly, is equivalent to so under some conditions, one can use them as substitutes for saying it is false or it is true respectively. We first observe some basic facts about derivability. Indeed, we can derive a BC using axiom 1, and then derive a Celsius by modus ponens twice from ax. 2. This follows from by the deduction theorem. If we further assume Celsius b, we can derive using, then we derive Celsius by modus ponens. This shows a C, a BC, CBC, and the deduction theorem gives a C, a BC, CBC. We apply X. 3 to obtain. Let Fahrenheit be an arbitrary fixed formula. For any formula, we define a F and a FF. Consider only formulas in propositional variables. Pn. We claim that for every formula in these variables and every truth assignment E, we prove by induction on A the base case A equal Pi is trivial. Let BC we distinguish 3 cases. 1. E equal 1. Then also E equal 1. We have CFF BCFF. By applying twice to the axioms since we have derived by the induction hypothesis, we can infer 2. Ed equals 0. Then again E equal 1. The deduction theorem applied to gives BFBCFF. Since we have derived by the induction hypothesis, we can infer 3. Ed equal 1 and E equal 0. Then E equals 0. We have a beginnerline to fertofictive to kavashko vertex b avash vertex b modus ponens enderline. Thus BFF by the deduction theorem. We have derived and by the induction hypothesis, hence we can infer this completes the proof of. Now let Fahrenheit be a tautology in variables. Pn. We will prove by reverse induction on K equal n that for every assignment E, the base case K equal n follows from a special case of using phi FFF and the fact that F is a theorem by the deduction theorem. Assume that holds for K plus 1. We will show it for K by applying deduction theorem to the induction hypothesis. We obtain a beginnerline IEP adots a PKIEP kavashbikato ferto FP IEP adots a PKIEP kavashbikato ferto phi enderline by first setting EPK equals 0 and second setting EPK equal 1. From this we derive using modus ponens. For K equals 0 we obtain that the tautology Fahrenheit is provable without assumptions. This is what was to be proved. This proof is constructive. That is, given a tautology, one could actually follow the instructions and create a proof of it from the axioms. However, the length of such a proof increases exponentially with the number of propositional variables in the tautology. Hence, it is not a practical method for any but the very shortest tautologies. Let's zoom in on the Bernays-Tarski axiom system and understand its implications. The Bernays-Tarski axiom system is often used. In particular, Ukasiewicz's paper derives the Bernays-Tarski axioms from Ukasiewicz's sole axiom as a means of showing its completeness. It differs from the axiom schemas above by replacing axiom schema 2 with axiom schema 2 which is called hypothetical syllogism. This makes derivation of the deduction meter theorem a little more difficult, but it can still be done. We show that from PK and PK one can derive per. This fact can be used in lieu of axiom schema 2 to get the meter theorem. 1. PK given 2. PK given 3. PK per ax 2 4. Krpermp 23 5. PK per ax 2 6. Krpermp 15 7. Permp 46 8. Per ax 2 9. Permp 78 10. Per ax 3 11. Permp 910. Turning our focus to satisfiability and validity, let's explore its key elements. Main tautology logic efficient verification and the Boolean satisfiability problem. Boolean satisfiability problem algorithms for solving SAT. Satisfiability in the implicational propositional calculus is trivial, because every formula is satisfiable. Just set all variables to true. Falsifiability in the implicational propositional calculus is NP-complete, meaning that validity tautology is co-NP-complete. In this case, a useful technique is to presume that the formula is not a tautology and attempt to find a valuation that makes it false. If one succeeds, then it is indeed not a tautology. If one fails, then it is a tautology. Example of a non-tautology. Suppose is false. Then obj is true, fk is true, off is true, d is true, and east is false. Since d is true, ft is true. So the truth of fk is equivalent to the truth of fe. Then since east is false and Fay is true, we get that Fahrenheit is false. Since off is true, A is false. Thus AB is true and Che is true. Co is false, so Celsius is true. The value of B does not matter, so we can arbitrarily choose it to be true. Summing up, the valuation that sets B, Celsius and D to be true and A, east and Fahrenheit to be false will make false. So it is not a tautology. Example of a tautology. Suppose obj is false. Then obj is true, K is true, D is true, and A is false. Since A is false, AB is true. So Celsius is true. Thus A must be true, contradicting the fact that it is false. Thus there is no valuation that makes obj false. Consequently, it is a tautology. In the upcoming section, we'll be shining a light on adding an axiom schema. What would happen if another axiom schema were added to those listed above? There are two cases. 1, it is a tautology, or 2, it is not a tautology. If it is a tautology, then the set of theorems remains the set of tautologies as before. However, in some cases it may be possible to find significantly shorter proofs for theorems. Nevertheless, the minimum length of proofs of theorems will remain unbounded, that is, for any natural number n there will still be theorems that cannot be proved in n or fewer steps. If the new axiom schema is not a tautology, then every formula becomes a theorem, which makes the concept of a theorem useless in this case. What is more, there is then an upper bound on the minimum length of a proof of every formula, because there is a common method for proving every formula. For example, suppose the new axiom schema were big. Then A is an instance one of the new axioms and also not a tautology. But A is a tautology and thus a theorem due to the old axioms using the completeness result above. Applying modus ponens, we get that A is a theorem of the extended system. Then all one has to do to prove any formula is to replace A by the desired formula throughout the proof of A. This proof will have the same number of steps as the proof of A. As we venture forward, let's examine an alternative axiomatization in detail and gain a deeper appreciation for its significance. The axioms listed above primarily work through the deduction metatheorem to arrive at completeness. Here is another axiom system that aims directly at completeness without going through the deduction metatheorem. First, we have axiom schemas that are designed to efficiently prove the subset of tautologies that contain only one propositional variable, a 1, where 2, obk 3, abiki obk 4, oba. The proof of each such tautology would begin with two parts, hypothesis and conclusion, that are the same. Then insert additional hypotheses between them. Then insert additional tautological hypotheses which are true even when the sole variable is false into the original hypothesis. Then add more hypotheses outside on the left. This procedure will quickly give every tautology containing only one variable. The symbol in each axiom schema indicates where the conclusion used in the completeness proof begins. It is merely a comment, not a part of the formula. Consider any formula that may contain a b, c, n and ends with a as its final conclusion. Then we take E5 as an axiom schema where is the result of replacing b by a throughout and is the result of replacing b by a throughout. This is a schema for axiom schemas since there are two levels of substitution. In the first is substituted with variations. In the second, any of the variables, including both a and b, may be replaced by arbitrary formulas of the implicational propositional calculus. This schema allows one to prove tautologies with more than one variable by considering the case when b is false and the case when b is true. If the variable that is the final conclusion of a formula takes the value true, then the whole formula takes the value true regardless of the values of the other variables. Consequently, if A is true, then and are all true. So without loss of generality, we may assume that A is false. Notice that is a tautology if and only if both and are tautologies. But while has distinct variables, and both have n. So the question of whether a formula is a tautology has been reduced to the question of whether certain formulas with one variable each are all tautologies. Also notice that is a tautology regardless of whether is, because if is false then either or will be false depending on whether B is false or true. Examples. Deriving Peirce law. 1. A 5-2. Per 1-3. Per 3-4. Per 23-5. 24-6. 51-7. Per 4-8. Per 3-9. Per 78-10. 29-11. Per 106. Deriving UK Civic Sole Axiom. 1. A 5-2. A 5-3. Peirce per 4-4. Peirce per 2-5. Peirce per 34-6. Per 1-7. Peirce per 3-8. Peirce per 67-9. Peirce per 58-10. 92-11. Per 4-12. Peirce per 3-13. Peirce per 1112-14. Peirce per 513-15. 1410-16, 151-17, Peirce per 318, Peirce per 617-19, 318-20, per 421, per 1920-22, per 2116. Using a truth table to verify UK Civic Sole axiom would require consideration of cases since it contains 4 distinct variables. In this derivation, we were able to restrict consideration to merely 3 cases: I is false and Q is false, I is false and Q is true, and I is true. However, because we are working within the formal system of logic instead of outside it, informally, each case required much more effort. I love interacting with my viewers, so leave me a comment and I'll do my best to respond.